Hello, welcome back to Learn Physics. In today's topic, we are continuing with the thermal properties of matter. In last class, we learned about the change of state. Till there we learned specific heat capacity, change of state, different states of matter, that is liquid, gaseous and solid state, all those things we learned, isn't it? So most of the portions you would have studied in the previous portion. Most of the lessons you studied in the small classes also, isn't it? Now we are going to study about the latent heat. What is meant by latent heat? Latent heat is the amount of heat energy required to change the state. Okay, for changing the state, how much heat energy is required? That is called a latent heat. So latent heat is the amount of heat energy required to change the state. For 1 kilogram of mass, if I am considering, what will be the change of state? And the heat energy required to change the state of the system. That means from solid to liquid or liquid to gas. To changing that one, what will be the heat energy required? That is called a latent heat. Okay, so latent heat, if we are considering solid as converting to liquid, for converting that one, how much heat energy is required? That is called a latent heat of fusion. Okay, the process is called fusion, isn't it? So this conversion is called as, the heat energy required is called as latent heat of fusion. And if the change is happening from liquid to gaseous state, then that is called a latent heat of vaporization. Amount of heat energy required to change from liquid state to gas or gaseous state, that is called a latent heat of vaporization. So in the case of water, while we are considering from solid to liquid, so we require 80 calorie per kilogram of joule for latent heat of vaporization in the case of water, and from liquid to gas it will be 540 calorie per kilogram. So it's not calorie, kilocalorie. 540 kilocalorie per kilogram, and this is 840 kilocalorie per kilogram. That is the latent heat, for the heat energy required to increase the state of, change the state. For 1 kilogram substance, we require this much of heat energy. For 1 kilogram of substance to change into vapor, then we require 540 kilocalories. So which one is more? For which process we require more heat energy? For latent heat of vaporization, we need more heat energy. That is why usually we will say the boiling water on the steam while we are considering, which is very harmful for us, see, harmful to the body. That is, if this burning due to this steam and burning due to boiling water, while both are considering, burning due to steam is more harmful. The reason is it includes this much of heat energy. So energy is more over there, so the effect also will be more. Okay, that is why it is too dangerous to get a steam burning, okay, than the boiling water. So if we are considering a graph between temperature and heat energy, this is temperature and this is heat energy. If we are considering the heat energy or temperature, and temperature in degrees Celsius while we are considering, see how the heat, see while we are giving, if I am considering water, and drawing the graph between these two, we know if from ice we are starting, from ice we will be getting heat energy and temperature will be rising and it will reach here and it will start melting. Melting will be starting. Here it is ice. Then during melting, heat energy will be increasing, but temperature remains the constant. Heat energy is increasing, temperature remains constant, and then what will happen when it becomes liquid? It will start accepting the raising the temperature will increase. Then it will increase when it starts boiling. What will happen? Again the temperature will remain constant and heat energy will be increasing, and then it will be converting it into gaseous form. Okay, this is what happening in the case of in gaseous form. Again temperature will be changing. Okay, so the heat energy will be remaining same in the case of when the melting starts. Okay, I start to melt. At that time heat energy will remain constant, that is 80 kilocalorie per kilogram. 80 kilocalorie per kilogram of heat energy is required to change from melting stage to converting purely into a liquid. Then this liquid again will be accepting heat energy and will start boiling. When it start boiling, after that it will remain constant. So here it is melting is at which temperature? It is 0 degrees Celsius and boiling is at 100 degrees Celsius. So this is what happening in the case of if we are drawing temperature heat energy graph. So only thing you should remember is the heat energy will be remaining constant. When it start melting, heat energy will be increasing and temperature remains constant. That is why we are telling the liquid and water and ice will be in thermal equilibrium with each other. So at the point of melting, when it is melting, they will be in thermal equilibrium. At the point of boiling, they will be, those two states will be in thermal equilibrium. That means temperature remains constant. So whether should we give the heat energy? Yes, we are giving the heat energy. That energy will be utilized for changing the state. Okay, it is not to increase the temperature. Okay, changing the state means it will be internal, molecular force of attraction will be changing. Okay, so the force of attraction will be changing. Okay, heat energy will be utilized for changing the state of the system. Okay, so clear all of you? So next we are going to study about the heat transfer. Okay, heat transfer means heat is moving from one point to another. How and all thus heat can be transferred from one system to the surroundings or surroundings to the system? How it is transferring? Okay, mainly there are mainly three types of heat transfer. First one is called a conduction. Conduction means, see, I'll give you one example first. I'm taking a small rod. Okay, and I'm heating at one end. I'm giving heat energy at one end. I'm holding it over here. After some time, I will feel that hotness, isn't it? The temperature, I'm feeling that hotness means the temperature at that end also will be increasing. But I gave heat energy only to the other end, isn't it? How the energy will be transferring from one molecule to another, like that it will be reaching to the other end. So this kind of heat transfer is called a conduction. That is, the conduction is happening without the actual movement of particles. Without the movement of particles. It is transferring from without the movement. That means it is transferring from one point to another. It is, it is like that of passing the parcel. Okay, we are giving the parcel to the next one and giving the parcel to the next one. Okay, so like that it is, that is called a conduction. So the heat transfer, rate of heat transfer, rate of heat energy is directly proportional to the rate of heat energy is directly proportional to the difference in temperature between the ends, and it will be directly proportional to the area. Okay, rate of heat transfer is directly proportional to the difference in temperature and directly proportional to area. So if I am keeping the rod AB, which is at a temperature TA at one end, TB at the other end, and this is thermally insulated, okay, at these two ends. Okay, what will happen if it is thermally insulated? That it is not moving outside, isn't it? So we can see that the difference in temperature will be TB minus TA. If TB is greater than TA, difference in temperature will be TB minus TA. So this will be directly proportional, rate of heat energy, and inversely proportional to the length of the rod. So rate of heat energy transferred is directly proportional to the difference in temperature. It is directly proportional to the area of cross section and inversely proportional to the length of the material. Okay, so the rate of heat energy is directly proportional to difference in temperature, area, and inversely proportional to length. So for changing the proportionality sign, multiplying it with a constant K, delta T into A by L. Okay, this K is called a coefficient of thermal conductivity. Thermal conductivity. Now we are going to find out what will be the unit of this coefficient of thermal conductivity. How we can find out? First we should write down the formula for thermal conductivity from here, that is H into L divided by A into delta T. H, what is H? H is the rate of heat transfer, heat energy. Rate of heat energy. Rate means with respect to time. So joule by second, time, right? So length is meter, area is meter square, delta T is Kelvin. So what we will be getting, meter square and meter will get cancelled, joule per second per meter per Kelvin. This will be the unit of K. Unit of K. Unit of K will be joule per second per meter per Kelvin. Okay, so rate of heat energy will be directly proportional to the difference in temperature. It is directly proportional to area and inversely proportional to length. Area of cross section, inversely proportional to length of the material. So that is why, see, H is proportional to delta T by A by L, and it is K is coefficient of thermal conductivity, and the rate of heat transfer depends on the material also. See, silver will be having very good thermal conductivity, and then copper also. Copper has very good thermal conductivity. Aluminium has very good thermal conductivity. That is why nowadays we are using copper bottomed vessel for our cooking, because copper will be absorbing more heat energy. Heat transfer will be more in the case of copper. Okay, silver also very good thermal conductor only. Okay, now see, if we are using a wooden rod, it won't be get a steel rod. If we have steel spoons and all, while we are using steel spoons and all, it will be it's easily, isn't it? Easily we can the heat will be transferring to the other end very fast. But if we are using wooden rod, it won't be getting, isn't it? It won't be getting heat at the other side very fast. Okay, so clear heat transfer, conductivity, conduction. Okay, next heat transfer we are going to study about the convection. Convection. Okay, next is convection. What is meant by convection? This is the heat transfer by actual movement of the particle. By the actual movement of particle, if the heat is transferring, then we can say it as convection. Okay, so how we can explain this convection? Convection means the particle will be moving. Because of the movement of the particle, we are getting convection. Okay, so the best natural phenomena which is occurring in the case of convection is the sea breeze and land breeze. How the sea breeze and land breeze are happening? See, when we are considering the daytime in summer season, while we are considering the daytime in summer season, the land will be very hot near to the sea. Near to the sea, the land will be very hot, because sea means water. It will be containing water. Water has very good specific heat capacity, so it will absorb more heat energy than land. So land will be getting very hot but sea won't be that much. Compared to the land, sea will be cold one. Okay, it's not cold, it will be, land will be very hot. If it is getting hotter, what will happen? Density will become less. If density is less, what will happen? This air near to the land will rises up. Land is getting hotter. When it is getting hotter, what will happen? The air molecules near the land also will be getting very hot. If the temperature increases, density will be decreasing. Then if density decreases, what will happen? It will move upward direction. So this space is vacant, right? So the cold wind from here, it will go to, from the sea, it will move to this land. So this process, so the wind is coming from sea to land. So this is called a sea breeze. The same way land breeze. How? In night time, what will summer season, night time, what will happen? See, land will become cool very fast compared to sea. So what will happen? Sea water is more hot, air will be there just above the sea water. So what will happen? This will go up. The density of the sea, the air above the sea water will be decreasing, and so it will move up, and the cold air from land, it will move to the sea. So that is called as land breeze. Okay, so this is actual movement of particles is happening in the case of convection. In our human body, if we are considering our human body also, that is what happening. Blood circulatory system also, since the blood is moving, thus we are able to maintain our body temperature throughout it as the same temperature throughout the body, isn't it? So that is what happening in the case of that, and all are examples for convection. And one more thing is trade winds. Okay, what are these trade winds? Trade winds are, say, in our earth, this is equator and this is the poles. Okay, this equator is more hot compared to the poles. So if it is more hot, what will happen? Air at this region will be, temperature will be more, so density will be less, it will move up. Okay, when it is moving up, cold air from that region will come down. Since the earth is rotating, it can't go till the poles. Before that itself, what will happen? Around this is the north region and this is the east region. Around northeast region, where this air will be falling down, that cold air will be coming back to that equator at a speed of 1600 km per hour. But in the poles, it is 0 km per hour. It won't be having that much wind over there. But at the equator, it is of 1600 km per hour. And this wind is called as trade wind. Okay, clear? These are the examples for our convection. Okay, next is third one is radiation. What is meant by radiation? It is the heat transfer without the medium. Medium is not required for the heat transfer. That kind of heat transfer is called as radiation. No medium is required for the heat transfer. Okay, so sun's heat energy. How we are getting sun's heat energy? It is because of the heat energy due to radiation. Sun is giving the radiation as electromagnetic waves. We are getting the sun's heat energy as electromagnetic waves. Okay, the same principle only we are using in the case of our thermos bottles, flask. In flask we are considering, we know outer covering will be an thermally insulated, and it is of dark colors or like that, something like that. So it will be reflecting the radiations, isn't it? If dark color means it will be absorbing the radiations, and if it is of light color means it will reflect the radiations, isn't it? So if I am taking a hot water inside the bottle, inside the thermos bottle, it will be covered with a double layered evacuated chamber. Okay, it will be covered like this, and a cork will be there at the top, and it will be having of light color. Light color means it will be reflecting all the radiation, all the light incidenting on it. And if it is dark color means it will be absorbing all the lights, all the radiations into it, coming into it. Okay, and it is evacuated also, so the radiation is not happening in the thermos flask. And if it is, since it is evacuated, conduction or convection won't be happening in the flask. Why? Because conduction and convection requires medium. Only radiation doesn't require medium, isn't it? Conduction. So if it is evacuated, no air is in between the walls, what will happen? Conduction won't be happening, convection also won't be happening over there. Okay, clear? This is what happening in the case of radiation. These are all about the heat transfer. Now in this chapter only a small portion is left out, that is Newton's law of cooling. That one I'll take it in the next class. So clear? All of you understood, right? So if you like the channel, please don't forget to subscribe. Thank you for watching. Bye.